Log on, tune in, find out. Another good idea from Cambridge.
Julia, who's going to talk about the science of exceptions.
So thank you very much for an invitation to be here. It's a very exciting time. And I try to make this title a little bit less mysterious and maybe not too ambitious. But I think it's quite important to go from a mood where one is saying that octonions are God to a scientific attitude where one is more looking for regularities and trying to extract from detailed analysis some precise consequences. So I will talk both about physics, but not so much about recent physics, although I think there are many important open questions there, and that's why I'm here. But I will mention, especially in some detail, an important topological problem where I think these ideas are important. And if you don't know about that, at least you will have learned some mathematics. So science is about classifying objects. Can you hear me? Yes. Studying their relations, classifying those, studying in turn their structure, that means the structure of the relations and so on, and more abstract levels of analysis. And the classification is to separate general cases or generic cases from exceptional cases or exceptions. So what is magics? Magics is a bad name, but it has been used recently, and you know the magic square of exceptional Lie groups. So it contains 4 of the 5 exceptional finite-dimensional Lie groups. And it has been called magical because it has very strange properties beyond just the definition. And the construction is quite interesting. It involves division algebras. I will mention that in detail. But also it has fancy properties like a symmetry about the diagonal, which at first was very mysterious. It's still a bit mysterious. But there is a symmetric construction of the magic square, so it's understood. But still, there are many miracles going on in this construction and many numerological properties that come together to make it work. That's about 60 years old. More recently, there was a magic triangle of supergravities that was actually discovered here in the Nuffield workshop in 1981, and a recent development using a non-supersymmetric version, but a split version that is looking only at the bosonic fields, can change the groups from some special real form to another real form. And so-called split real forms of finite-dimensional Lie groups are the maximally non-compact form. That's what physicists call maximally non-compact. Mathematicians call them split. And they are, in a sense, forgetting the difference between the real and the complex. The complex are important to diagonalize matrices. If you are split, you can do that over the real, so everything is much simpler. But I'm going to argue that magic square magics lies also in the real properties, and it has not been studied enough. So I will discuss that. So the square involves, you will see in these slides some tables where you have groups, and the matrix has of course, 2 coordinates. One is the dimension of space-time in the case of the magic triangle, and n is the number of quartets of supersymmetric charges. So it's very strange. Before, the 2 lines were the division algebras, lines and columns were division algebras. Here, one line is dimension, and the second line is consecutive dimensions, and the second line is spinors in 4 dimensions. So if you want the symmetry, it will be also a symmetric triangle, and the symmetry will be between 1 bosonic dimension and 4, the opposite actually of 4 supersymmetric dimensions. So -4 Fermi dimensions. So just to make sure that you're not confused with the so-called magic squares you may have seen before, these magic squares are such that the sums on the lines, columns, and diagonals are equal. And this one, I don't know who had the idea of doing this, but they are consecutive primes. So if you have time to waste, you can do that. But I will not talk about this. Supermagic triangle. So this split form of the triangle that was discovered in 81. So here you see some table with, as I said, the dimension here from 11 to 3. I will not discuss lower dimensions because the groups become infinite dimensional and I lose my classification framework. Maybe the classification framework will have to be changed, but at the moment I have nothing to say so convincing about the rest, so I will not talk about that. And here are, as I said, the supersymmetry number. So this actually 7 supersymmetries, or, which gives automatically 8. This is 6 quartet of supersymmetries, 5 and so on, up to here, which is 4 dimensions. So you have n equals 8 supergravity, n equals 6, 5, 4, 3, 2, 1, and 0. So this triangle is 8 by 8, and diagonal. And the square has been discovered by these people. Freudenthal, a German living in Holland, and Jacques Tits, a Belgian living in France. So that's Europe. And here is the magic square in a complex form without choosing any real form of the groups at the moment. And as you see, it is two-dimensional. It's 4 by 4, and it contains the groups E6, E7, E8, symmetric across the diagonal. It contains also F4 and C3, or USP3. These two groups are so-called non-simply laced. So that's a problem for me, because if I go back to here, all the groups here are simply laced. So for instance, here A1 is SU2, E2, this little x is a cross, sorry. R is the real numbers, and there is no F4, no G2 in this supersymmetric context, at least for those theories of pure supergravities. And okay, as I said, G2 is missing. So here are two questions comparing these two tables. First, why do we need 2 dimensions? One speaks about magics in this 2-dimensional setting. Usually one has also exceptions in 1 dimension, as I will argue, but one doesn't, they do not deserve the name magics. And secondly, the tension between these two was, in the supersymmetric supergravity case, I had the only ADE type diagrams, simply laced Lie groups. And these are very frequent. I will discuss that later in the talk. But in the magic square, one has to do something to get rid of the unwanted F4 and C3. So are these things crucial, or what should be said? So first of all, the 2-dimension of the magic square of groups of Tits and Freudenthal is actually obtained by combining 2 lines, and one algebra in a line and the division algebra in the column. So respectively R, C, quaternions and octonions, and the same here. And there is a uniform construction of all these Lie algebras choosing a pair of 2 division algebras. In fact, there are at least 2 constructions. So the so-called composition algebras, people are, of course, very familiar. If you have questions, I can answer them, but I will not have so much time to discuss those. So people are, I assume they are familiar with what octonions are. In physics now, most people have to know about SO8, and triality, and octonions. And the 2 constructions are sketchily explained here, first by Tits and the second by Winberg. There were also arguments using geometries due to Rosenfeld, Freudenthal, but the construction are using division algebras were these 2. So the first one, so A and B are the 2 division algebras to be chosen. So it's you know, in classification of Jordan algebras, the 3 by 3 Hermitian matrices are very special, and especially the one over the octonions was discovered in quantum mechanics. So you take these 3 by 3 matrices, make a Jordan algebra with that, and you combine, take the tensor product with the other one, take the derivations of this Jordan algebra, derivation of the second algebra. I didn't write the rules, so you have to combine all these to make a Lie algebra, and the answer is the magic square. Now, this is absolutely not symmetric in A and B, and the result is symmetric in exchange of A and B. Why? Well, let me go to the Winberg construction. There is a symmetric construction which is similar but a little bit different. So you take the tensor product of 2 composition algebras or division algebras, A tensor B, and derivations, and this is how Winberg constructs the same, now obviously symmetric magic square. So if you go to real forms, as I say, Tits very long ago had classified the real forms for his choice, for his construction, and I discussed that with him. And I was interested in this because, as you may have noticed, here you have the 3 by 3 magic square in the triangle, here, right? So this is very mysterious. There is no F4, so it stops there. But and we have very specific real forms. Here, these are the split forms, but in supergravity theories, I will show you the real forms. They are very specific, and unfortunately, the TILS construction doesn't give for any choice of real forms uniformly on the columns and on the lines. Apparently, unless I made some mistake or I made some mistakes, do not reproduce the real forms of supergravity. So it's an open problem which should be solved. And now we have much more expanse. So I just wanted to mention that because there was some work of Barton and Sudbury who also discussed real forms, and they didn't actually recover the forms I needed for the same reason. But they didn't seem to be aware that TILS had done the same before. So we are in dimension 1. So if you classify exceptions, usually you have in a good case, you have a few exceptions. And there is no order, there is no notion of dimension. So you have isolated another set of exceptions, so dimension 0. Now let's look at the classification of real simple Lie groups. As you know, you have 3 infinite families, SON, SUN, and USP2N. Take the compact forms for choice. So these are the notations. G as the rank, as an index, and usually the signature, which is the number of non-compact generators minus compact generators, as a number here to distinguish various real forms. So if the signature is the same as the rank, then the complex rank is equal to the real rank, is equal to the signature, is called the split form. Maximally non-compact real form of a group. So these are infinite series, and E6, E7, E8 are exceptional because there are only 3 of them. There is no infinite series. Where does it stop? We will see that later. Still, there are orders, so there is kind of a beginning of an ordering set of exceptions. Let's continue. So one obtains these 3 families, and then, as one notices, this corresponds to orthogonal conditions over the reals, the complex and the quaternions. So are the octonions responsible for the exceptional groups? In a sense, yes, but it's more complicated and it's not precise. So I don't want to spend my time saying we should study the octonions. I mean, of course, we have to study the octonions, but I want to be more precise. So En are still ordered, but G2 and F4 are 2 isolated exceptions. In fact, I will quickly drop G2 and F4 because they're not simply list. And as I said, in the ADE problem called ADE by Arnold, they don't appear at the first stage. So I will not discuss too much ADE singularities, but in ADE singularities, Arnold has classified and listed a large number of occurrences of these, especially the Carter matrices of these ADE groups that occur in very many places. And they are not isolated, of course, because the AN and DN are on a line, but the ENs also are connected to the others. There is a diagram where singularities can flow to each other, and it's a connected diagram. So E6 flows to D5, as we will see. It's the same in the next construction in supergravities. And but the two-dimensional structure is much more, it's like a graph, it's not a matrix. So let me begin the talk. So we should count exceptions in some cases, so when they are not too frequent, and why should we do that and how? So in physics, we should define and classify. So we set up a problem, a context, and within these rules, we play the game and we classify. We look for instance, for polytopes, tilings, crystals, space symmetries. If you add these more sophisticated symmetries, you have classifying U-dualities. So I will not distinguish between continuous U-dualities and discrete ones. Actually, I will only talk about continuous ones, and the arithmetic study is much more involved. It's related to another discussion of exceptions, which I will not enter. And supersymmetries also are classified in the context of realistic models. As we will see, there is a finite number of interesting type of supersymmetries. M-theory is a very special exception. And there are more classifications one can do. Real division algebras, I will mention those. These correspond to the lines and the columns in the magic square. Real simple groups, we have discussed those. Finite simple groups, they correspond to implementing again the real simple Lie groups over finite fields. But there are some exceptions of several types, infinite families, and there are the famous sporadic groups, which I will not discuss too much, but certainly one doesn't know how to see them in this division algebra picture, or they somehow they are related and not far from the E8 and exceptional groups and octonions, of course, but there is no unified understanding of all the sporadic groups. So, and then the last topic I want to discuss is totally different. The problem of division algebras was studied at the end of the 19th century, and in 1930, 1940, it entered the field of topology, and the god here is really Heinz Hopp and his students who developed this interplay between parallelizability of spheres and division algebras and such things. And there was very important progress 2 years ago. So exceptional will mean finite number, at least a relatively small number. So for instance, ground states in a bounded volume, you want some discrete conditions, so you need a compactness condition of some inequalities, and I will show you some that are important. And secondly, to make it interesting, you of course want these exceptions to be useful. For instance, to have special properties like divergence-less, integrability, or uniqueness, like a maximal theory of supergravity or supersymmetry with 16 or 32 supercharges. So, but now I want to find some systematics in the exceptions, so I want to recognize structures. So, of course, if you have no order, besides the cardinal of the set of exceptions, it's not very interesting. If you have some order, it becomes more interesting. So order is usually one-dimensional counting. You have no natural order in higher dimensions. So you can count all the way to 4, or you can count all the way to 8, depending on if you're interested in the square or the triangle. But you have to choose, and they're not the same. So who is answering which question, or obeying which counting, that's the goal of my talk. So if I look at the divisional algebras, I have 4 of them, the real complex quaternions and octonions. And they have dimension 1, 2, 4, 8 over the reals. If you shift that by 2, you have the famous 3, 4, 6, 10 dimensions of super Young Mills. And the number of supersymmetries is, if you want, 1, 2, 3, or 1, 2, 3, 4, because you can shift arbitrarily. You can also count to 3 to get E6, E7, E8. They appear, as we have seen, in the 3 by 3 square inside the 4 by 4 square of Tietz and Freudenthal. They are also related to Platonic solids, so to discrete subgroups of SO3. And one might think that they are actually belonging to a triplet. In fact, Arnold wants to assign them to a trinity, but I couldn't understand his reasoning, and I checked. He attributes this idea to Kazhdan. I just wrote to Kazhdan, and he didn't explain. So I'm not sure I agree with this statement. That so the trinity for Arnold, I will not discuss more this subject, but is a triple of objects where the second is obtained by complexification of the first, and the third is obtained by quaternionization of the first one. And in a sense, E6 is associated on one direction to the complex, that quaternion and to octonion, so you complexify it twice, but it's more like this is associated to complex, this quaternion and this octonion. So it's very imprecise. So maybe I should skip that. So you can count lattices. This is for another talk where I could make the sporadic groups fit into the analysis. To classify finite Jordan algebras or superalgebras, you also find some special role for octonions. Finite superalgebras, the thing I want to say is that there doesn't seem to be any special role of E groups. There are 2 anomalous, exceptional finite dimensional superalgebras, which are more like F and G, and or variants of F and G. So it's a bit of a mystery, and maybe the conclusion of my talk will be that we are missing a lot of understanding on the Fermi side. So I personally have spent more time than I should have, probably on the bosonic aspects and the ordinary symmetries. But the supersymmetries are very important, and they are where the mystery lies. So that was counting up to 4, but there are 2 instances where one should definitely count all the way to 8. So the first one is the so-called theory of Del Pezzo surfaces. these are two-dimensional complex surfaces, so real dimension 4 manifolds. There are finite surfaces, so finite manifolds is a generalization to higher dimensions, and finite surfaces is just the same as Del Pezzo, so if you see the name, you shouldn't be surprised. And never mind the definition, but they are kind of very simple, very symmetric, not symmetric, but very special complex surfaces, and there is a finite number of them. In fact, there are 10 of them. So there are CP2 and CP2 with k points blown up, so with 1 to 8 points blown up. So from 0 to 8, that's 9 such manifolds. And one more, which is CP1 cross CP1. And these are related to the string theories. So actually to M theory compactified on a torus. And this is related to 2B theory. CP2 is related to M theory, and CP21 to 2A theory. I will come back to that. So this was discussed by Waffa and collaborators. This was actually noticed and he told me about that 30 years ago. By mining this, the person who studied the cohomology of these manifolds is Yuri Manin. And when I showed him the triangle, he said, this looks like what I have found. But today, it's still a mystery why these two things are the same. There are connections, but it's very mysterious. So what happens in these surfaces is that the middle cohomology, so these are four-dimensional real manifolds. Middle cohomology is two-dimensional. It has Lorentzian metric, and it's space-like part, so there is a special time-like direction. And the orthogonal complement, which is d-1 dimensional, so in the cohomology, is the root space of a complexly algebra, namely Ek, but Ek where k is allowed to vary between 8 and 0. Actually, there is one more, which is A1 corresponding to this special CP1 cross CP1. So before I was advocating that E6, E7, E8 is a nice set of exceptions, but here I'm telling you that in a different set of problems, En is a nice set of exceptions. And in the case of triangle, of course, you had the ENs. We'll see them again on the longest line and on the longest column. And in the magic square, you couldn't get beyond, of course, E8, and you couldn't get below F4 on the wrong side. So there's something...
This was the first column in your big table, right? This is a column in the triangle.
Yes, and also the line. I'll show you again. So this is the magic, so these are actually split forms that occur in the physical theories, where you start from M theory or supergravity in 11 dimensions, and you compactify on maximal tori. And the maximal torus you can use is a dimension to go to 3. If you go beyond, then you get these affine and hyperbolic structures, which are interesting also. And you get this E8, E76, but also E5, which is D5, E4, which is A4, A1 cross A2, R cross A1, R or A1. R is for coming from 11 dimensions, and A1 is the 2B case. And here, what is totally mysterious, and that's why I use the word magic in 1981, that if you do the same for n equals 6, 5, and so on supergravities, pure supergravities in 4 dimensions, which had been constructed, I remind people who were not born at the time that these supergravities were constructed starting from n equals 1, painfully to n equals 4 with a couple of scalars. And then it was very difficult, and we jumped to this theory by using a suggestion of Nam that maybe there was a theory in 11 dimensions that was possible and that could be related. Also, it was not obvious without using triality and very detailed things that one couldn't be sure of, that this 11-dimensional theory should be related to that. So we, instead of constructing the complicated theory here, we constructed it there, and going down, we obtained it directly. So here I just want to show you that these are actually split forms because this split form of the triangle, but in the case of supergravities, these are different real forms. So this E7 is not the same as that one, this E6 is not the same as that one, and so on. So why is it symmetrical? Or once you complexify, why is it symmetrical? Nobody knows. So let's compare 8 and 4. So inside the EK series, you have E6, E7, E8. So in the first case of counting to 4, I mentioned that there is a connection with division algebras, RCHO and Young-Mills and Green-Schwarz superstring. We return to that. In this case, it's connected to supergravity, so closed strings. So it's closed, it's open squared in a sense, but it doesn't appear as open squared at the moment. It would be nice to find a way to do that, but I don't know how to do it. And there is a interesting remark that SL2 over the division algebra A are universal covers of these groups corresponding to this dimension 3, 4, 6, 10. For SO91, it's a little bit more subtle, so people are still working on this to clarify it. But there is, for instance, a recent paper by Huerta, where he covers this. It's a series of papers, actually, where he gives a review of previous works. And so I would say the counting up to 4 has been quite fully exploited. The counting up to 9 has not been exploited. So what I want to say is that the counting up to 8 occurs at the moment in the Del Pezzo classification and the supergravity classification. And we'll try to see whether it can be applied to some other cases as well. So to classify, you have to generalize, compare. It's kind of geology. It's not like mathematical physics. You just have to look at many different objects. If they are very technical and very complicated, you pretend you understand and you just have a first idea of what these objects are and try to organize them in a nice whole and nice collection. And then once you have formulated a nice question, you can go deeper. And for instance, my last part of my talk will be about differential topology. This is very technical. I think now I'm motivated to go deeper into understanding that, and I hope I will motivate you to also discuss with your colleagues in the field. And then, of course, in a later life, one can make more abstract categorical analysis and try to prove things at the level of across the fields in a kind of categorical way, but I will not do that here at all. So part 2 is a very quick reminder of what ADE problem R is. So in 76, Arnold formulated the so-called ADE problem, which is, roughly speaking, why do the Coxeter groups or why do the Cartan matrices of simply laced Lie algebras occur in so many places and finally dimensional simply laced algebra, and what can we do about that? So first of all, I want to stress that the fact that you get a Coxeter matrix somewhere or a Cartan matrix doesn't mean the full group is acting, because it's true that starting from a Lie group one gets a Cartan matrix, but conversely, it's not always obvious. There is one case, for instance, which has been studied earlier by Briscorn, following a suggestion of Grothendieck, which makes a precise relation between a Lie group and singularities, for instance, which is one instance of the ADE problem, which will be classified, singularities will be classified by the Dynkin diagram. And so the correspondence of Briscorn shows that within a given group, some singularity of a uniform type that doesn't depend on the group will be classified by the same Dynkin diagram as that of the group. So these two things are really related, but not equivalent. It's not because you have a crystallographic group that you have the Lie group automatically. So the Platonic solids, everybody knows them. The symmetry groups, they are same for 2 pairs. So there is actually only 3 different groups here. And there are the infinite families for the dihedral symmetries, which are actually 2-dimensional. So the groups, subgroups of SO3 are so-called tetrahedral group, octahedral, and icosahedral. There are permutations of 5 alternating group in 5 elements, symmetry group in 4, alternating in 4. They correspond to Dynkin diagram or Cartan matrices of E6, or more precisely in so-called Mackay correspondence, the affine group of E6 occurs to make it really convincing. Affine extension of E7, affine extension of E8. And the Coxeter groups, I emphasize, are not the same as the subgroups of SO3, are respectively A3, BC3 type, and H3. So these ADE, of course, combined in 2 families now. I have only AN and DN, plus 3 exceptional E6, E7, and E8. The Cartan Coxeter matrices occur repeatedly. Why? And I just want to make as a comment that I also already mentioned the fact that I didn't want C3 and F4 to stay in my discussion because I don't see them immediately in the supergravity discussion. Here also, you can have singularities where the Bn, Cn, and F4 diagrams appear or Cox-Torter groups appear, but they are usually coming in the second step. You do a classification problem and then you add an extra condition like add a boundary in the acoustics problem, then you get the BC F4 groups. Actually, it seems that naively you don't get the G2. I'm sure you can, by adding one more condition, you certainly can get the G2, but as there is only one, it's not very interesting. But okay, so ADE tends to be simpler to achieve. It corresponds to symmetric Cartan matrices than the others. So why do we get a finite set of E diagrams? Well, as I said, you need some inequalities to make the problem compact to have a finite set of solutions, or it is finite in some directions. And here is the difference between AN, DN, and EN. You can consider the different Dynkin diagrams of these groups. AN is just a line, DN is a fork, and EN is a fork which is not quite the same. And the question is, why can't you grow this leg as much as the others, that is up to infinity? And the reason is just technical, but it's very simple to see. If you compute the determinant of, you have a two-term recursion relations, and the determinant of the AN Dynkin Cartan matrix is actually 2, 3, 4 starting from A1. For DN it's constant, and for EN it decreases, because the first two are just in the right order, so that you start from determinant 6, you get determinant 1 for E8, and determinant 0 for the next one. And I remind you that if E8 is here, then if you add one more, you get the affine extension of E8, and it's at determinant 0. And this is not allowed in classification of finite dimensional groups because you have this positivity that says that the Cartan matrix has to be positive. In particular, the determinant has to be positive. So just for your general knowledge, I already mentioned the Platonic solids, but there are many other instances of the ADE problems, representations of quivers, which people have used extensively in physics, singularities of algebraic hypersurfaces. I will mention that a little bit. Classification of critical points of functions having no moduli, either of functions or also Lagrangian, in the context of Lagrangian problems, which give the same classification for some mysterious reasons. And the classification of Cox-Torter groups in the case of equal length roots. So for instance, the singularities of type E8 and E4 are given by these equations. And you look at the point at the origin here, and you have the exponents 5, 3, and 2, which are familiar for E8, and for A4 you get also 5, 2, and 2. In physics, we also have some inequalities which allow us to generate exceptions. If you have no conditions, there is no exception. Everything is a solution. So I want to show you precisely these conditions that we impose that give the same result as the conditions I mentioned in the case of Lie groups. So it's not obvious why it's the same, but it is actually what we need. So for the open case, for the Young-Mills case, of course, we need that n is at most 4. So you get angular momentum at most 1, and at most 4 supersymmetries. For angular momentum at most 2, you get n at most 8. And again, I mentioned that before, closed resembles open squared. And that I already said. So let me now go to a comparison of these different triangle and square in more detail. So quaternions or octonions were born in 1983, and both actually, but published in 1845, as people now know because it has been well told by John Baez, for instance. So I tried to focus my discussion on the distinction between counting all the way to 4 and counting all the way to 8, but one could make a more general have a more general philosophy and say whenever there is an octonion, this is an exception or this is especially interesting. So first of all, it's too wide, and second, I'm missing some subtle points because in both cases 4 and 8 octonions are at play, so I want to distinguish them and I want to have a final analysis. So what is known, one has classified the so-called division algebras, which are finite dimensional division algebras with unit, which are such that 0 has no divisor, and over the reals there are only 4 solutions, but this has been proved in steps and only recently, in fact, in complete generality. And there is an important restriction which is related to compactness. I will not explain that in too much detail, but either you assume that it's finite dimensional or you may assume that it has a unit element. And the unit element in the algebra corresponds to the compactness of the function domain. So G2 is the automorphic group of the octonions, F4 is the automorphic group of OP2, of the Jordan algebra, special Jordan algebra of 3x3 matrices over the octonions. And RP2, CP2, HP2 have corresponding automorphic groups. I will mention them later. So here's another magic, but in physics. This has been actually constructed by Paul Townsend, and it's still being studied, for instance, by Gunaydin to study the gaugings in his theories. And I want to show you the real forms because they correspond to, in fact, real forms of the Tits-Freudenthal magic square. So instead of taking the normal so-called compact forms of the division algebra, both in the lines and the column, here you take the normal form, the compact form of the octonions, but vertically you take the split form of all the 4 different algebras. And for some reason, here you get a non-symmetric square, and you get very nice relations and many properties that are worth mentioning, like for instance, the fact that in a group, in a non-compact Lie group, you have a maximal compact subgroup, which everybody knows. But what not everybody knows maybe is that you also have a maximal split subgroup. So that is the split subgroup is the one for which the Cartan torus is maximal. So if you have a maximal Cartan torus, non-compact Cartan torus in some group, is there a simple group inside containing this Cartan torus that is maximally non-compact inside this group? That has been studied. And it turns out that in this line, the maximal non-compact subgroup or maximal split subgroup is F4. And here this column is the fourth column is always split forms. C3 is a maximal split subgroup of these 3 forms, A2 and A1, again split. Okay, I can explain many details as things, the rank changes, the signature changed by 1, the real rank changed by 1. There is a so-called gravity line appearing. When you start from higher dimension here, you compactify in a larger and larger tori, so you make a SLN appear, or GLN, and this is reflected by the Dynkin structure, in fact the real Dynkin, the real structure of the Lie group. And this applies also in that case. So these, I just wanted to finish by saying that these are the automorphic group of OP2, HP2, CP2, and RP2. So here is a truncated version of the precise super U-dualities of truncated, of dimensionally reduced maximal supergravity and its lower supersymmetry versions. So in 4 dimensions, what you have is a pure supergravity with various numbers of supersymmetries. As I said, if you have 7 supersymmetries, it guarantees automatically you have 8. And here you have the column I had before, the split En, so the 8 Ens. And here you have a, contrary to the split form, you have to stop because this is not maximally split. It's not maximally non-compact, so it has a smaller non-compact torus, and you can only generate a GLD of compactification up to here. Same here, same here. So the 3x3 magic square is not completely there. And as I said, the real form is not even present. So the fact that there is one group missing tells you that the magic square construction cannot really work, because otherwise it would predict symmetry here, or maybe trivial symmetry. So this is the story of the dualities. I don't want to tell you too much about that. So to remind you of the time frame, the mathematics, of course, comes much before physics. Del Pezzo was 1887, but it took about 100 years for mining to go to the root system. So progress is slow, and it was quite a big change between progress between this classification and the appearance of root systems, which I claim again is not deeply understood. It's just observed in this work. In the case of division algebras and composition algebras, so composition algebras is not quite the same as division algebras, but they turn out to be the same in finite dimension. It corresponds to the fact that you have a norm that's multiplicative, and as this story has been told many times, so quaternion, you know what it is, for octonions also. And the difference between the different real composition algebras is that first two are commutative and associative. The octonions are non-commutative and associative, and the quaternions are non-commutative and associative, and the octonions are not even associative. So the classification actually came in steps because the octonions were not so familiar. So the associative algebras were classified first by Frobenius and Weierstrass, and Hurwitz came at the end, where he found the fourth one, allowing for an alternative composition algebra. And topology entered, so that was the end of the 19th century, and topology entered with Hopf in 1940. So the so this is a one-dimensional magic. You can to 8 and you can to 4, and the four-dimensional structure came 50 years later, some shift, and for physics 30 years after so the triangle is 30 years younger than the magic square. So here are the two heroes of counting up to 8. Some more details on homology. That is a very bizarre property of Del Pezzo surfaces. You have I will use this structure in the case of the Kerber invariant, so we can practice on that. You have a four-dimensional manifold, so the middle cohomology is dimension 2, or homology also, and you have an intersection form, or in the dual, the cup product, which makes an intersection form on the cohomology, which tells you if you have two forms, you can integrate the wedge product on the manifold and you get a number. And this form, this quadratic form, is, in the case of four-dimensional manifold, a symmetric form, and it's a metric. And it has signature Lorentz, one time direction and d-1 space direction. And as I said, the root lattice of En for all these n values or 10 values of Del Pezzo correspond to the orthogonal to the one particular cohomology class called the canonical class K, which is time-like. And so I already mentioned that in 11 dimensions you get CP2. Then in 10 dimensions you get CP2 with 1 point blown up, or CP1 cos CP1. And in 9 dimensions, sorry, the next one corresponds to 9 dimensions is CP2 with 2 points blown up, or CP1 cos CP1 with 1 point blown up. And the fact that these two theories correspond to one here is just a mathematical statement of T-duality in this context. So to summarize, we need to understand better the real forms, and I feel bad that I didn't finish it yet, because there are very simple things one must do. For instance, I think Winberg has not classified the real forms for his construction, and it has to be done, and I want to understand better if I can make contact with the 3x3 magic square of Thyssen-Freudenthal and the triangle. Also, it's not completely clear to me how to go from the 4x4 magic square to the 3x3 magic square, because as I said, one want to eliminate F4 and C3, and so one line and one column, and that amounts to drop not E8, not the octonions, sorry, but the reals. So that means, in a sense, going to the complex forms, forgetting about the reals, saying they are special, like as I said before, the case of F4 and C3 singularities in the Arnold phenomenology came as by imposing some special folding, like a boundary or some orbifold or some extra structure. So here, if you stay complex, you just drop the last line and last column on the magic square, but this has not been justified completely precisely. And in particular, I want to understand what it means when you go precisely to the real forms, why you still prevent this F4 to appear. So this is a simple problem to work on. Just want to mention one more triangle which is due to Cvitanovich, about the same time as the supergravity triangle. And it's different. It's closely related to the magic square. It extends the magic square. It includes F4, but it's not related to more than to our triangle. And now it's the last part of my talk about the topology. So Hopf was really a fantastic person. He didn't write many papers, but each of them is very deep. Furthermore, his list of students is extremely impressive. So if you have no time, I mean, if you have some time to spend reading interesting stuff, I suggest you read his complete works, and I'm sure you will get some nice ideas.
How many volumes does that run to?
Just one.
Just one.
Yeah. So I want to make a comparison between one solved problem, which is for which the British community was very efficient, so-called Hopf invariant 1 problem, and the second problem, for which the American community was very efficient, so-called, actually, both of them were, Hopf school was very important at the beginning, but recently the most progress was done by the American school. And I feel very embarrassed because it's like bringing coal to Newcastle. I'm not a topologist, it's extremely technical, I don't know much about the subject, but I disagree with the intuition of some people, so I'm looking forward for confrontation discussions. On the other hand, these people don't have the same rules as physicists. For instance, there's somebody by the name of Marcel Böckstedt who has nice ideas about the magic square, and Atiyah himself has some ideas about the magic square in that context, but they don't want to discuss. So I don't know what to do. I can go and pest them. And so anyway, it's very dangerous for a Frenchman to go to the UK, especially to cross a road. But here, to do topology is extremely dangerous. But I will tell you a few things, and maybe you can go back and study more and discuss. But I'm here for 10 more days, so I think we have time to make progress. And I have some specific questions. In fact, some of my ideas can be falsified. So it's not like a speculation, it's very precise. The trouble is that it's very technical, so you have to spend some time to check whatever, and I will just formulate the problem. So Hopf is very well known, so you know the Hopf vibration. It's quite important for physics, for the Möbius strip, for the monopole charge. So let me focus, for instance. So these are vibrations of S2n minus 1 over Sn, the fiber Sn minus 1, and what is special is that S1, S3, S0, S1, S3, S7 are special because they correspond almost to groups. For instance, S3 is SU2, and S7 is not a group, but it's related to octonions in so-called H space, and it's the only other sphere that is parallelizable, like groups are. So these are quite special objects, and the question is what is special about them and how to study them. So one thing that has been invented by Hopf is counting the invariant. For instance, in the case of the monopole, you know that the S1 fibers are linked to each other, and in the monopole charge 1, the linking number of two fibers is 1 or minus 1. So this is an integer, and it can take the value 1 in this case. So, sorry?
You asked me what S0 was.
0 is 2 points.
2 points.
So up to the normalization constant, which I don't want to discuss, the Hopf invariant is very simple to define. Sn is has a volume form which is closed because it's maximal dimensional. So you can pull it back to here, which is an n form, and you integrate on S to n minus 1 Fn times its primitive a. So f is dA because f is closed still on S to n minus 1, and this gives you the Hopf invariant. So the question is the following: can one reach value 1 for this invariant or not? Because it can be shown that either it's 0 or it's only multiples of 2, except for 4 cases, which is for the 4 cases I mentioned, n equals 0, 1, 3, and 7. Sorry, n minus 1 is n is equal to 1, 2, 4, and 8, so n minus 1 is 0, 1, 3, and 7. So for n equals 8, S7 is very special. It was discovered by Milnor that it has 27 other exotic differential structures, and it's parallelizable in the usual one by this kind of analysis. So let's go a little bit more general to what is known about the topology of spheres. It's frustrating that we don't know the homotopy groups of spheres up to today. The problem about homotopy groups is that they don't stop at the dimension of the sphere. So for instance, in some cases we know, but in some other cases we don't know too much. Even we know only for very small dimensions, in fact. So for if n is odd, there is no more infinite. So one can distinguish torsion, so-called finite homotopy groups, Z2, Zn, or products of those, and infinite homotopy, which is Z, so infinite factors. And the so-called tensor product with Q is just a fancy name to say one drops torsion, one forgets all the finite order elements in the homotopy group, and one replaces Z by Q or R if one wants, and one gets something much more computable. Torsion is next order of difficulty. So if you look only at the torsionless part, one can show it was shown by Serre in 1951, I think, that pi 0 of Sn and pi n of Sn are both Q or R or Z up to torsion, and there is no more. If n is odd, if n is even, I just showed you that pi 2n minus 1 of Sn is Q, and that can be proved. And the question is, over Z, there is a certainty in the normalization. It can be Z or 2Z. That is the value 1 appropriately defined reached or not? And it's Z and not 2Z for, again, these values, 1, 2, 4, and 8. If you look at the proof, it's fairly obscure. I mean, you require arguments like you want 2 to the k to divide 3 to the k minus 1. And that gives you that list. So one has solved the problem, but one is really in the magic domain, I think. So another way to make this a bit more simple to understand and to understand the normalization is to say, let's consider the 2n dimensional disk. Its boundary is S2n minus 1. If you have a map from S2n minus 1 to Sn, you can use that map to glue Sn to the n. So you have a complex with a dimension 2n object plus dimension n, so the cohomology of that has indeed some dimension n part. And inside this cohomology, you can do this cup product I was mentioning before, because n is the 1/2 of 2n. So you can take the cup product of hn and hn over 2z, because I said one is interested in the parity. So if one wants to realize 1, it just means that we are looking for this modulo 2, and we want this to be non-zero modulo 2. Okay? So when you look at these cohomologies, and the next part of the final part of the talk will be about Z2Z cohomology. And this cup product is in H2n, and the coefficient of the relation between that and the volume form has a scalar number, which is a Hopf invariant. So what is it good for? It involves, in fact, many different things. This series of 4 fibrations and its special values of n correspond to many properties, like the unit spheres are parallelizable. The bundles involve the projectile lines over these algebras, like for S3 modulo U1, you know that you start from R4, you take the sphere, then you quotient not only by the modulus, but also by U1, then you get CP1. And CP1 is S2. And you get a generalization for the other division algebras. So a simple proof of this set of 4 exceptions is, after a very long proof by Adams, was found by Atiyah using complex K-theory and these very bizarre arguments. But the proof is 2 pages, where the technical proof, as I said, the field is very technical, was 60 pages before. So K-theory was developed, in fact, for that purpose, the complex K-theory. And it led also to the solution of vector field problem, which I will skip because I have no time, which counts the number of independent vector fields on spheres, which is using real K-theory now, but which is another big success of these Hopf ideas. In physics, these division algebras, which are behind the scene, as we have seen, are related to the Young-Mills model, so Brink, Schwarz, Kourou, Townsend, Evans contributed to that, and it's becoming popular again. I just want to say that the key identity seems to be this trilinear identity in the context of supersymmetry, but the deep understanding of that is not completely clear. The discussion, for instance, of Kugo and Townsend was about the fact that if you have a supersymmetric sigma model and you start from a dimension 6, 4, or 3, you end up with a Riemannian, Kählerian, or hyper-Kählerian structure. It was not so clear what the result is when you start from dimension 10. I would like to propose a definition of a Youngian sigma model, maybe, or an integrable sigma model. This is still to be studied, I think. I want to emphasize that in the case of the closed analog, I mean going to the triangle and going to supergravities, again the Fierce identities are very mysterious. For instance, for 11-dimensional supergravity, the Fierce identity certainly makes SP32 play a very special role, which is not more understood than this. And I'm suggesting that one should try to copy this in the case of supergravities. So, as is already clear here, the role of supersymmetry is still not sufficiently central and well understood in this context. The point is that spinors don't stop at n equals 8. What stops at n equals 8 is the interacting theory, the fact that you cannot afford to have spins higher than 1, and for some reason this has not been digested. Let me finish with the Kerver invariant. So just a reminder about Stiefel-Whitney classes. There are homotopy groups with values in Z over 2Z for real manifolds. So for instance, orientability corresponds to W1 is equal to 0. The existence of spin structure to W2 is equal to 0, the second Stiefel-Whitney class, which is sufficiently complicated to define it so that I don't want to do it here. And in fact, so if W2 is equal to 0, if H2 is big, you have many non-trivial spin structures. It essentially counts them in a non-canonical way, but so you want the obstruction to be 0, but then if you have a big H2, then you can have many spin structures. Spin C structures are related to another property. So Kerver is now a field of study important for differential topology. So people are interested, for instance, in the Poincare conjecture for differential manifolds, or differential structure on the spheres. And as you know, Milnor has found this 28 differentiable structure of S7 in the 50s. And it's still not known how many differentiable structures there are on S4. And it's quite related to the homotopy groups of sphere, or stable homotopy group of spheres. And this Kerver invariant is a very important object to make progress on this discussion. So let me give you a few examples of where it has been used and historically. Very early on, well, it was called ARF invariant before, so I call it the ARF Kerver invariant here, but apparently Kerver didn't know about that, so he didn't quote ARF, and it's now called Kerver invariant, but never mind. And the ARF invariant, as Arnold would say, was called ARF because it was discovered by Dixon, but that's another story. So we are talking about the existence of an obstruction, or the existence of differentiable structure ds on a compact manifold. So for instance, S10 has 6 differentiable structures, whereas Kerver constructed a manifold in 10 dimensions in 1960, which has none, which has a kind of tour de force to prove that something has no differentiable structure. I mean, find one differentiable structure is hard enough, but prove that there is none is very tricky. And he had a fantastic discussion, which I'll try to mention here. So for information, S2, S3, S5, S6, and S12 have only one differentiable structure. S4 could have an infinity of them. It's not clear. So again, on M, so the Kerver invariant is kind of the analog of the signature invariant, but on the dimension 4n plus 2. Signature is defined for manifolds, Euclidean signature, with manifold dimension 4n. So the middle dimension H2n plus 1 with coefficient Z to Z supports an antisymmetric bilinear form S, and one refines it by choosing a quadratic form Q, such that this is true. So this looks a bit bizarre, but as you know, except in characteristic 2, if 2 is invertible, giving a quadratic form or a symmetric form is the same. you can just use this and define a product of U and V by 2 times capital Q of U and V equal to that. If 2 is equal to 0, this doesn't define anything, so one can try to define S by this. And the question is, can you find Q so that this is true given S? And then the half-Kerr invariant for your information is, there are many properties, but Q can take value 0 or 1, and the K invariant of a manifold is the majority value of the Q's for all the points on the lattice. So the quadratic form is actually defined by some extra structure which I didn't mention, which is essentially framing of this manifold M. Well, there are many technical conditions, stable framing and various things I will easily skip over. And the binary number of 0 or 1 is the cobordism invariant. That is, if you have 2 manifolds which are the boundaries of the same manifold with trivial tangent bundle, then the Kerr invariant is the same. So it corresponds to the class of cobordism manifolds. So Kerr topological sphere, so not to be confused, the 4n+2 manifolds I was talking about before, is obtained by plumbing or explicitly. So if you don't know plumbing, it's the intersection of this 4n+3 dimensional sphere and the germ of, or the inverse of this singularity. So you look at this hypersurface in 2n+2 complex dimensions, and this has dimension 4n+1, 4n+2 real, and the intersection with S4n+3, this is sigma 4n+1. So result, which is highly non-trivial, that sigma 4n+1 is non-exotic, so it has it is diffeomorphic, not only homomorphic to S4n+1. It's always homomorphic to S4n+1, but it's only diffeomorphic to it in dimensions 1, 5, 13, 29, 61, and maybe 125. Sorry. And okay, there are some tricks by gluing sigma 4n+1 to a disk to construct manifolds with Kerr invariant 1 and so on. And this is, you can see the strategy now, but so my question now is, I want to make contact with what I said before, so can you recognize these numbers? Can anybody tell me what these numbers are?
Powers of 2 minus 3.
Yes. Did you know the answer? Or? You're very good. So I'm not as fast. So my first. So my first reaction was I didn't find these numbers because in another set of results, the dimensions that appear are 2, 6, 4n+2. Just one more is these numbers. So when I was given these numbers, I couldn't find this 2 to the n-2. So I said, well, but I knew that people had been mentioning the magic square, like Atiyah, for instance. And in fact, this started because John McKay wrote me a letter, as he writes a message, and he does that every other year, so urging me to go to a conference in Edinburgh. So I never go, but I look at the program, and I discovered that there was this activity on Magic Square. And I still don't know what Atiyah said, but he promised to put it on the web, but he hasn't put it yet. So anyway, these numbers, I looked at these numbers, and my first reaction, as I'm pretty biased, of course, is to say that this is the number of roots of E7, right? Now, these are the number of roots of the groups on this line. E7 is here. So I want, my story is, I have a finite number of exceptions. I want to find the same list of exceptions somewhere. So it would stop maybe here. So these dimensions, number of roots of these 4 elements, is again exactly what is needed. But here I'm wrong by a factor, by 2. So it works, but almost. And then I realized that, of course, if there is an accident here, because I didn't, well, I can show you. Here, you see the subgroups are SO16, SO12 times SO3, SO10 times SO2, and so on. So it's SO2 as a factor. These are emission symmetric spaces. This is quaternionic. And then the SO3 fuses, so the symmetry becomes much compact, much more symmetrical. So I said this accident here was probably related to the fact that this is SO3 and not SO2. And then I banged my head and said, of course, this is 2 to the n. So now we know, everybody here knows that the dimension of these crossed spaces here is exactly 128, 64, 32, and so on, all the way down here, right? So then, because you have to subtract 4, these two terms don't appear, so you may have a reason why you would get 6 solutions in the natural context. So, okay, this is neurology and that's very deep, but still there is one more step of information. One more piece of information I want to give you, and I will conclude with that. Sorry, I want to give you here. But I skipped a couple of slides. Okay, I have no time to explain too much about the construction of Kerver, but in fact, this 2 to the n is famous in the field because Browder, when he was classifying the manifolds such that the Kerver invariant was 1 and not 0, obtained this condition that the dimension had to be, so it's a necessary condition, not sufficient, 2 to the m minus 2. So the 2 to the m was there and the minus 2 also. So it's only once you have that you feel that spin-offs or division algebras should be brought to bear, but not exactly division algebras because there are certainly 5 or 6 terms. Now, the theorem that has been proved beyond Browder is the theorem in 2010 by Hill and 2 more Americans, Hopkins and somebody else, who proved that the Kerver invariant 1 dimensions were precisely 2 to the m minus 2, but only those, and maybe that one. So the proof for this was to exhibit the examples, or prove the existence by some concrete argument. Beyond that, the next one and all the others would be excluded by some very complicated topological arguments, some generalized K theory, KO theory, in fact. And let me give you some idea of what these manifolds are and why you can easily prove that dimension, for instance, 2, 6, and 14 are applicable. Because in a sense, the Kerver invariant is the square of the Hopf invariant, at least for this, and the manifolds you should consider are precisely S1 cross S1, S3 cross S3, and S7 cross S7, which gives you this dimension 2, 6, and 14. The next one would be 2 times 15, so it's not one of the Hopf category.
It is.
Sorry?
It is.
It's not alternative, yeah. Well, okay.
Well, S15 is a vibration of S7 by S8 by S7.
Yeah, well.
But then it stops there.
Okay. Yes, right. So yeah, I think Hopf will not be enough. And most exciting is that the next one in dimension 30 has been shown by some very complicated argument due to Marcel Buckstedt, and it's unpublished. I just found his name and his results, or some of his results, looking at transparencies of talks of other people on the web. So because the experts will not tell me, but I tell you. And it's related to, so the 30-dimensional one is related to that. Now, if you remember, this is precisely the group here. And now these people believe that the magic square is involved, but actually not everybody believes that. So I think ATR, so I'm reconstructing, but I didn't check with him, he didn't send me his notes, so I don't know exactly what he has in mind, of course. He claims, they probably claim, and I've seen that in print, but not attributed to anybody in particular, that this, beyond this space, these 3 spaces, which are in fact related to the magic square of Kitz and Freudenthal, not to the triangle, should be related to these. I'm not sure I understand it. Finally, this manifold is related to S7 to the 4 by some complicated construction. And this one doesn't know whether it exists. So if I am right, I would think that this manifold is actually Kerver invariant 1, because I want to go all the way to E8. And in fact, after I formulated that conjecture, I looked at a talk by Hopkins, where he presented his results in front of Atiyah and Wheaton. And the question by Wheaton at the end is M126 related to E8? And there was no answer. Okay, so we finish here. So we need a magician, and a guy who is magician is Skirm. So it's for Nick Manton. It's a nice picture of Skirm, and he proved that bosons are fermions, so maybe fermionic dimensions are minus bosonic dimensions.
Who's that, Kevin?
No, this is Skirm.
Skirm?
Skirm.
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 Oh, just Skirm.
Skirm, yeah.
Well, where did you get that picture?
From the web. You have to live with your time.
Long hair.
Okay. Thank you.
Any quick questions? Leonard is here a while. Obviously.
I have some problem imagining a manifold that isn't differentiable. I mean, so it's global, right? So there has to be some chart where the overlaps, the one set of coordinates against the other one are not differentiable functions.
Yes, I think in the particular case of this non-differentiable manifold, you take the disk of dimension 10 and you glue this S9, but by a continuous map, not by a differentiable one. And the singularity can be removed. If it were removable, you could show that the Cava invariant would have to be 0. That's the idea.
So if you tried to put a metric on it, the metric could be continuous, but there would have to be a discontinuity.
There's a singularity. Yeah.
It has a brane on it or something.
That's right. There's a singularity.
Okay, let's thank speak again.